Hello, and welcome. This is Quiet Knowledge. Take a slow breath in and let it go. Wherever you are right now, whatever you have been doing today, you can set it all down for a little while. There is nothing you need to hold on to, nothing that requires your attention in this moment. You have given enough of yourself to the day. We are going to go somewhere together, somewhere ancient and enormous and very, very still. We are going to spend some time with the Milky Way, not the version of the Milky Way from a science textbook, full of numbers and diagrams and things you are expected to remember, just the real one. The one that has always been above you, whether you could see it or not. The one that was there the night you were born and will be there long after every name has been forgotten. There is something deeply comforting about that. So let us begin, slowly and quietly, the way the universe itself began. Imagine for a moment that you are lying on your back in a wide, open field. The ground beneath you is soft and cool. The air is still. There are no buildings nearby, no streetlights glowing orange on the horizon, no sounds of traffic or conversation. Only the gentle movement of the earth, breathing through the grass around you, and above you, an enormous dome of darkness filled with light. You are looking at the night sky. On a clear night, far from the glow of cities, you might be able to see somewhere around 2,000 stars with your naked eyes alone. 2,000 individual points of light, each one a sun of its own, each one impossibly far away and yet present to you. Visible, real. You could spend a lifetime learning the names of those stars and still find new ones waiting. But when your eyes have had time to adjust to the darkness, something else appears. A pale, faintly luminous band stretches all the way across the sky from one horizon to the other. It is not made of individual stars you can distinguish. It looks more like a soft brushstroke of light, a smear of something luminous and diffuse, as though someone drew a gentle line across the sky with a finger dipped in diluted moonlight. That band is the Milky Way, or rather, it is our view of the Milky Way from inside it. What you are looking at when you see that pale river of light is the combined glow of hundreds of billions of stars so far away that your eyes cannot separate them into individual points. They blur together into something soft and continuous, like the way a distant forest looks from a mountain, not individual trees, but one green, breathing thing. Human beings have been looking at that band of light for as long as there have been human beings. Every culture on Earth has had a name for it, a story for it, a feeling about it. The ancient Greeks called it the Galaxias Kyklos, the Milky Circle. From that word, Galaxias, comes the word we use today, galaxy. And from the Roman version of the same idea comes the name we know best, the Milky Way, the road of milk, across the sky. For most of human history, no one knew what it was. It was simply there, beautiful and unexplained, something to wonder at on clear nights and return to in memory on cloudy ones. It was not until the early 17th century that an Italian astronomer turned a simple telescope towards that pale band and saw, for the first time, that it was made of stars. Galileo Galilei, looking up at what had always been a soft blur, suddenly saw it resolve into something else entirely, a field of countless individual stars packed so closely together that they merged into light. That moment, that quiet Tuesday night in Padua, or wherever he was standing when he first pointed his instrument at the sky and saw all those stars, must have been something extraordinary. Not terrifying, not overwhelming, just quietly, profoundly astonishing. And what he was seeing, though he could not have known it then, was the edge-on view of the galaxy we live inside. He was looking through the disk of a spiral galaxy from within the disk itself, like an ant standing inside a vinyl record and looking toward the center. We still do exactly what Galileo did. We still go outside on clear nights and look up at that soft band of light. We still feel something when we see it, even now, even after all we have learned about what it actually is. There is something about the night sky that slows the mind down. Astronomers have a word for the sky conditions needed to see the Milky Way clearly. They call it Bortle dark sky scale, and the very darkest places on Earth, the places farthest from all human light pollution, are rated as Bortle class 1. In those places, the Milky Way is so bright that it casts a faint shadow. It is bright enough to make objects on the ground dimly visible. The zodiacal light, a different kind of celestial glow caused by sunlight reflecting off interplanetary dust, is so bright in Class 1 skies that inexperienced observers sometimes mistake it for the beginning of dawn. Most people alive today have never seen a Class 1 sky. More than 80% of the world now lives under light-polluted skies. For a third of humanity, the Milky Way is simply invisible, hidden beneath the orange haze of city lights. Children grow up without ever seeing that pale river above them, and yet it is there. It has always been there. It will be there tonight if you can find a dark enough place, if you are willing to wait for your eyes to adjust, if you give the sky a little time. The universe does not rush. It simply continues steady and ancient and unconcerned with your schedule. There is something restful in that. The night sky asks nothing of you. It does not require you to be any particular kind of person. You do not need to understand it to find comfort in it. You can lie on your back in that imagined field and simply look, and that is enough. The stars do not grade you on your comprehension. They are simply there, burning slowly, the way they have been, burning since before anything on this planet could look up and notice them. Let us look a little closer now. Let us try to understand where we are. The Milky Way is, to put it simply, our home. Not home in the small sense, the way a house or a town or even a country is home. Home in a much larger, quieter sense. The Milky Way is the structure of gravity and gas and stars and dust that contains our solar system, our sun, our Earth, everything we have ever known or will ever know, every person who has ever lived and every person who ever will. It is all here, inside this one galaxy. And our particular location within that galaxy is a place astronomers call the Orion Arm. The Milky Way, like many galaxies, is shaped something like a pinwheel. It has a bright central hub, and from that hub extend long, curving arms of stars and gas and dust that spiral outward. Our solar system lives in one of those arms, a medium-sized one called the Orion Arm, or sometimes the Orion Spur. We are not in the center. We are not at the very edge. We are somewhere in between, roughly 2/3 of the way out from the galactic center towards the outer rim. If the galaxy were a large city, we would be in a quiet suburb, a pleasant neighborhood, far from the busy, crowded center, with its flashing lights and constant activity. Our distance from the galactic center is roughly 26,000 light-years. A light-year is the distance light travels in a single year. Light moves at about 300,000 kilometers per second, which means, in a single year, it covers almost 10 trillion kilometers. So 26,000 light-years is a distance so large that numbers become nearly meaningless. It is simply very, very far. But here is the quietly comforting thing about that distance. It means we live in what astronomers sometimes call the galactic habitable zone. The center of the galaxy is a turbulent, energetic, crowded place. Stars are packed closely together there, and there are frequent supernovas, violent explosions of dying stars that release enormous amounts of radiation. the intense radiation near the galactic center would be harsh to life as we know it. It would make it difficult for planets like Earth to sustain the calm, steady conditions that seem to be needed for life to develop and persist over billions of years. The outer edges of the galaxy have their own challenges. Out toward the farthest reaches, the gas and dust needed to form rocky planets and complex molecules becomes thin and sparse. The ingredients for life as we understand it are harder to come by. But where we are, roughly 2/3 of the way out, is a kind of middle ground, not too close to the intense, turbulent center, not so far out that the ingredients for life become scarce. A comfortable, quiet address in a large and varied structure. Astronomers sometimes compare this position to the habitable zone around a star, the so-called Goldilocks zone, where a planet is neither too hot nor too cold for liquid water. Our position in the galaxy is something like the Goldilocks position of the galaxy itself, not too close to the center, not too far away. We sit in a kind of cosmic calm. There is another thing worth knowing about our location, something that adds to its quiet, settled feeling. Our solar system sits in a region of the Orion Arm that is relatively low in density. We are not surrounded by a dense, crowded cluster of stars. We are in a somewhat open, spacious part of the galaxy, with room around us in most directions. Our nearest stellar neighbor, the Proxima Centauri system, is about 4 light-years away. In galactic terms, that is not very close. In human terms, it is incomprehensibly distant. But by the standards of densely packed regions near the galactic center, we are in a quiet, uncrowded neighborhood. Think of it like this. If you were standing in a large, ancient library, our solar system would be somewhere in the reading room, away from the busy circulation desk, not in the far corner where the collections are sparse, but comfortably in the middle ground, surrounded by the quiet, orderly presence of books and the soft light coming through tall windows. It is a good place to be. It is, in fact, the only place any of us have ever been. We tend to think of home as something we chose, something we made or arrived at by intention. But we did not choose our position in the Milky Way. We did not decide to be born in the Orion Arm, 2/3 of the way out from the center, in a quiet suburb of a spiral galaxy in a small group of galaxies on the edge of a vast supercluster. We simply arrived here the way everything in the universe simply arrives at where it is, carried by the slow, patient currents of gravity and time. And it turns out to be a very suitable place. Describing the size of the Milky Way is one of the places where ordinary language starts to soften and blur at the edges. The Milky Way is approximately 100,000 light-years across. Some estimates put it slightly larger, perhaps 120,000 light-years in diameter. Its disk, the flat, spinning region where most of the stars live, is thought to be about 1,000 light-years thick in most places, though it thickens toward the center. These numbers are true, and they are also nearly impossible to hold in the mind. So let us try a different approach. Let us try to feel the size of the galaxy rather than understand it. Imagine that you are holding a grain of sand. A small, ordinary grain of sand, the kind you might find on any beach. So small, it barely has weight in your palm. Now imagine that this grain of sand represents our entire solar system, from the sun to the outermost edge of the Oort cloud, the vast spherical shell of icy objects that marks the boundary where the sun's gravity begins to lose its hold. The Oort cloud extends roughly 1 to 2 light-years from the sun. So this grain of sand represents something like 2 light-years in diameter. Now, if that grain of sand is our solar system, how big would the Milky Way be? It would be roughly the size of the continental United States. Your solar system, your sun, every planet, every moon, every asteroid and comet and spacecraft we have ever launched, all represented by one grain of sand. And the galaxy that contains all of it, an area the size of the entire continental United States, from the Atlantic to the Pacific. Take a slow breath. There is no need to feel small in a distressing way. This is simply what the universe is like. It is large in the way a forest is large, in the way the ocean is large, in the way deep time is large. Not threatening, just vast. And within that vastness, the things that exist are extraordinarily varied and complex, and, in their own quiet way, beautiful. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range is wide because counting the stars in our galaxy is genuinely difficult. We cannot step outside the galaxy and count them from a distance. We are inside, looking around, trying to estimate the whole from a partial view. It is a little like trying to count every tree in a forest while standing in the middle of it, in the dark, with limited visibility in most directions. Astronomers use a variety of methods to estimate the number of stars, including measuring the total mass of the galaxy, estimating how much of that mass is in the form of stars, and accounting for different types of stars at different sizes. The answer they arrive at is something in the range of 100 to 400 billion. The middle estimates tend to settle around 200 to 250 billion. 250 billion stars. If you were to count them at the rate of 1 per second, without stopping, without sleeping, it would take you nearly 8,000 years just to count to 250 billion. 8,000 years. Ago, the Sumerians were developing the first writing systems. Stonehenge had not yet been built. The Great Pyramid was still 4,000 years in the future. And you would be only partway through the count. This is not meant to be dizzying. It is meant to be settling. There is something almost meditative about numbers that large. They carry you beyond the reach of ordinary anxiety. Nothing that is bothering you today, no problem, no worry, no difficulty, exists at the scale of 250 billion stars. At that scale, everything human becomes very, very small, and in its smallness somewhat easier to hold. Let us also think about the mass of the galaxy, the total mass of the Milky Way, including its stars, its gas, its dust, its planets, and the mysterious dark matter that surrounds it, is estimated to be somewhere around 1 trillion times the mass of our Sun. The Sun itself has a mass of about 2 times 10 to the power of 30 kilograms. A number so large it simply requires a moment of peaceful acceptance rather than comprehension. 1 trillion of those. All of that mass spread over an area 100,000 light-years across, slowly turning, slowly breathing in and out over billions of years. The galaxy moves very slowly on a human timescale. It does not feel urgent. It does not feel pressed for time. It has been doing what it does for more than 13 billion years, and it will continue for billions more. There is no sense in the galaxy of anything needing to be accomplished before a deadline. That, perhaps, is the most calming thing about the Milky Way. It operates entirely outside of rush. If you could leave the Earth and travel upward, high above the plane of the galaxy, and look down, you would see something remarkable. You would see a disk of light, glowing softly in the darkness, with a bright, slightly thickened center surrounded by long, graceful arms curving outward and away from the core. The arms would be traced in blue-white, light where young, hot stars are burning, and in softer gold and orange where older stars live their longer, quieter lives. The Milky Way is a barred spiral galaxy. The word barred refers to the fact that at the center of the galaxy, instead of a simple round hub, there is a long, elongated structure made of stars called a bar. This bar extends across the core of the galaxy and connects at each end to the beginning of the spiral arms. From above, it would look a little like a slow, luminous propeller. The major spiral arms of the Milky Way have names. The two main arms, the ones thought to begin directly at the ends of the central bar, are called the Scutum Centaurus arm and the Perseus arm. These are the largest and most prominent of the arms. They curve around the galaxy in long, graceful arcs. Our solar system lives in a smaller arm, sometimes called the Orion arm or the Orion spur, which branches off from one of the larger arms like a smaller creek branching from a river. The Orion arm is not one of the great sweeping arms of the galaxy. It is a more modest structure, a shorter, thinner feature between two of the larger ones. There is something quietly ordinary and satisfying about that. We do not live in the grand central boulevard of the galaxy. We live on a side street, a quieter thoroughfare tucked between two larger structures in a perfectly comfortable and unremarkable location. The spiral arms are not solid structures. This is an important and somewhat surprising thing to know. The arms are more like waves than they are like objects. They are density waves, patterns of slightly increased compression that move through the disk of the galaxy the way a ripple moves across water. Stars do not stay in the arms forever. They pass through them the way cars pass through a slow-moving area of traffic on a highway. Imagine a long stretch of highway with a slow-moving section caused by a gentle bend in the road. Cars bunch up slightly as they slow down in that section, and then spread out again as they move through and continue. From a great height, you would always see a cluster of cars in that particular spot, even though the specific cars in the cluster are constantly changing. The spiral arms work in a similar way. The arms are regions where the density of gas and dust is slightly higher, where the gravitational pressure is slightly greater. As stars and clouds of gas pass through these regions, the increased pressure causes the gas to compress. Compressed gas can collapse under its own gravity. When it collapses, it forms new stars. This is why the spiral arms appear bright and blue-white. They are regions of ongoing star formation. The arms are where new stars are being born, and young massive stars burn hot and bright and blue-white before they live out their shorter lives. The spiral arms, then, are something like nurseries. Slow, enormous nurseries where gas and dust are gently urged into collapse and new suns are kindled in the darkness. Our solar system has probably passed through several spiral arms in its long lifetime. It drifts slowly through the disk of the galaxy, passing in and out of regions of greater and lesser density, carried along by the slow gravitational dance of the whole structure. Right now, we are between arms. We are in the quieter zone between the Sagittarius arm on one side and the Perseus arm on the other. We are in a region of lower star density, a slightly emptier stretch of galactic space, like traveling through the countryside between two cities. There is something peaceful in that image. The galaxy is not homogeneous. It has busy regions and quiet ones. We happen to live in one of the quieter ones, at least for now, at least in galactic terms. The spiral structure of the Milky Way has been something astronomers have worked to understand for a long time. Because we are inside the galaxy, it is difficult to see the whole shape clearly. It is like trying to understand the architecture of a building from inside one of its walls. We can measure distances, observe the patterns of gas and dust, track the movements of stars, and from all of that slowly build up a picture of the overall structure. That picture is still being refined. New data from telescopes and observatories continues to add detail and nuance to our understanding of the galaxy's shape. There is something reassuring in that too. The Milky Way is so large and complex that even our most sophisticated instruments are still working to map it fully. It remains in important ways a mystery we are still gently unraveling. The universe does not give up all its secrets at once. It reveals itself slowly, the way a landscape reveals itself as morning fog gradually lifts. At the heart of the Milky Way, roughly 26,000 light-years from where we are, is a place that is very different from our quiet suburban neighborhood. The galactic center is bright and dense and energetic. Stars are crowded together there at extraordinary density. Clouds of gas and dust swirl in complex, turbulent patterns. Strong magnetic fields thread through the region. The light and radio waves and X-rays coming from the galactic center tell astronomers that something very massive and very powerful is sitting at the very middle of all of it. That something is a supermassive black hole. Its name is Sagittarius A star, written as Sagittarius a star and usually pronounced Sagittarius A star. It sits at the exact gravitational center of the Milky Way, and it has a mass of roughly 4 million times the mass of our Sun. 4 million solar masses. A black hole is a region of space where matter has been compressed so densely that the gravitational pull becomes strong enough to prevent anything, not even light, from escaping. For light to escape a gravitational field, it must be moving fast enough. A black hole is simply a concentration of mass so extreme that even light, moving at 300,000 kilometers per second, is not fast enough. This can sound frightening on the surface, but consider it more gently. Sagittarius A star is 26,000 light-years away from us. That distance is so enormous that the black hole's gravity, powerful as it is near its own center, has absolutely no special effect on us here at Earth. We are not being pulled toward it in any meaningful way beyond the ordinary gravitational influence of the galaxy as a whole, which simply keeps the entire structure rotating slowly together. The black hole does not reach out into the galaxy like some enormous hand. Its extraordinary gravitational power is concentrated very close to itself. From our distance, it is simply a very massive object at the center of our galaxy, affecting the orbits of stars near it, generating interesting physical phenomena that astronomers study, but not in any way dangerous or threatening to us. Most large galaxies are thought to have a supermassive black hole at their center. This seems to be a common feature of how galaxies form and evolve. The black hole at the center of the Milky Way is, by some standards, a relatively modest one. Some galaxies have central black holes billions of times the mass of the Sun. Ours, at 4 million solar masses, is considered fairly typical for a galaxy of the Milky Way's size. In April 2019, astronomers released the first direct image of a black hole, the one at the center of a galaxy called Messier 87, about 55 million light-years away. It showed a glowing ring of orange and gold light surrounding a darker central region. The image was assembled from data collected by a network of radio telescopes positioned at observatories all around the world, a collaboration that effectively created a telescope the size of the Earth to resolve a feature so small and so far away. Then, in 2022, the same collaboration released an image of Sagittarius A star itself, our own galactic center black hole. It too appeared as a soft, quietly at the center of everything. The quietly at the center of everything. The image took years of work to produce. Imaging Sagittarius A star was in some ways harder than imaging the black hole in Messier 87, because the galactic center is so crowded with gas and dust that the light has to pass through a great deal of material to reach us. The astronomers had to carefully account for all the interference, the way a person might carefully wipe away fog from a window to see through it clearly. The result was quietly stunning. The central black hole of the Milky Way, seen for the first time, glowing in its ring of heated gas, sitting at the heart of everything. Stars near the galactic center orbit Sagittarius A star in the same way that planets orbit a star, but much faster because the central mass is so enormous. Some of these stars, called S-stars by astronomers, have been observed completing full orbits around the black hole. The closest of them, a star called S2, orbits Sagittarius A star in just 16 years, moving at speeds of up to nearly 3% of the speed of light at its closest approach. These close, fast orbits were, in fact, what allowed astronomers to measure the mass of Sagittarius A star. By watching those stars move and applying the same laws of gravity that govern the motion of planets in our solar system, they could calculate what kind of mass must be at the center to produce those orbits. It was one of the more elegant confirmations in the history of astronomy. Ancient gravitational laws written by Newton and refined by Einstein applied to the very center of our galaxy, and finding there a black hole of 4 million solar masses. The center of the galaxy is busy and complex and energetic, but from our perspective, it is simply a distant point of interest, the way the center of a large city might be to someone living quietly in the countryside. It exists. It has its own character and rhythms, and we can observe it from a comfortable distance with curiosity rather than concern. Stars do not appear suddenly. They grow slowly, the way everything in the universe seems to grow, over timescales that make human patience seem momentary by comparison. The process begins in the places called nebulae, which is simply the Latin word for clouds. Nebulae are regions of the galaxy where gas and dust are gathered together, sometimes in loose, sprawling structures that stretch across light years of space, sometimes in denser, more concentrated knots. When you look at photographs of nebulae taken by telescopes like the Hubble Space Telescope or the James Webb Space Telescope, you often see something that looks almost like landscape, like mountains and valleys rendered in light and shadow, in deep purples and blues and golds and reds. These images, while not always in the colors our eyes would see, are based on real data about the actual structures of these clouds. They are genuinely that beautiful. Within these clouds, the gas and dust is not perfectly uniform. There are regions that are slightly denser than others, tiny gravitational seeds where the pull of gravity is marginally stronger. Over long periods of time, these seeds attract more material from the surrounding cloud. More gas falls inward. The density slowly increases. As the density increases, the gravity increases, pulling in more gas, which increases the density further. This is called gravitational collapse, but the word collapse makes it sound sudden. It is not sudden at all. It happens over millions of years. A slow, patient gathering in of material, a gradual thickening of gas into something that begins to be called a protostar. As the gas collapses inward, it heats up. Gravity converts the potential energy of infalling material into heat. The protostar grows warmer at its core. The temperatures rise, the densities rise. And eventually, over hundreds of thousands of years, something remarkable happens. The temperature and pressure at the very center of the protostar become high enough to trigger nuclear fusion. Hydrogen atoms, which have been gathering together under the increasing pressure and temperature, begin to fuse together into helium. This fusion releases an enormous amount of energy in the form of light and heat. That energy pushes outward against the inward pull of gravity. When the two forces, the outward push of nuclear energy and the inward pull of gravity, reach a kind of equilibrium, the star settles into a stable state. At that moment, a star is born. Our own sun went through this same slow process about 4.5 billion years ago. Before the sun existed, there was a cloud of gas and dust, and before that cloud collapsed, The atoms in it had already been through extraordinary journeys. Much of the hydrogen in the Sun is primordial, created in the first minutes after the Big Bang. But the heavier elements, the carbon and oxygen and iron and silicon, were created inside previous generations of stars, stars that lived and died before our Sun was even a protostar. The atoms in our Sun and the atoms in the Earth and the atoms in every human body have traveled through stellar furnaces. When you look at the night sky and see the stars, you are looking at structures made of the same material you are made of, arranged differently, under different conditions, burning at different temperatures. You share a common chemistry with the stars. Not metaphorically, literally. The calcium in your bones was forged in a supernova. The iron in your blood was made in the core of a dying star. Astronomers sometimes say, "We are made of stardust." It is one of those phrases that has been repeated so often, it has become a kind of cliché. But it is still true. It was true before it was a cliché, and it will be true long after the cliché has faded. Stars form throughout the Milky Way, but most actively in the spiral arms, where the density waves compress the gas and trigger the gravitational collapse. There are regions of the galaxy known as giant molecular clouds, where star formation is most active, enormous reservoirs of cold, dense gas that are the primary nurseries of new stars. One of the closest active star-forming regions to our solar system is in the constellation Orion. The Orion Nebula, visible to the naked eye as a faint smudge in the sword of Orion on a clear night, is a region where new stars are being born right now. At this moment, as you read or listen to this, there are protostars in the Orion Nebula that are slowly gathering mass, slowly warming, slowly progressing toward that moment when fusion begins and a new sun is kindled. It will take hundreds of thousands of years for some of them to become proper stars. But it is already underway. There is something deeply peaceful about that timescale. The stars are patient. They do not hurry. The universe tends its own processes at its own pace, unhurried, unconcerned with deadlines, simply allowing things to unfold in the time they require. The Milky Way is forming new stars at a rate of roughly 1 to 3 new stars per year. This is actually a relatively modest pace. Some galaxies, called starburst galaxies, are forming stars at rates hundreds of times higher in great violent bursts of stellar birth. The Milky Way, by contrast, is a calm, steady galaxy, forming its stars at a gentle, sustainable pace. It has been doing so for most of its existence, and it will continue doing so for billions of years to come. 1 to 3 new suns every year somewhere in the galaxy, kindled slowly in clouds of ancient gas. The universe itself is approximately 13.8 billion years old. That number comes from a variety of independent measurements, the most powerful of which involves studying the cosmic microwave background radiation, the afterglow of the Big Bang, a faint, uniform hiss of microwave radiation that fills all of space and carries within its tiny temperature variations, a detailed record of conditions in the early universe. The Milky Way is nearly as old as the universe itself. The oldest stars in the Milky Way, found in structures called globular clusters that orbit the galaxy like slow satellites, are estimated to be about 13 to 13.5 billion years old. These stars formed very early in the history of the universe, within the first few hundred million years after the Big Bang, when the raw materials for galaxy formation were first settling into the gravitational wells that would become the large structures we see today. Think about what that means. Some of the stars in our galaxy have been burning for 13 billion years. Our Sun, at 4.5 billion years old, is a relative newcomer. When our Sun was forming from its cloud of gas and dust, Some of the stars in the Milky Way's globular clusters had already been burning for 9 billion years. They were ancient before our sun was born. The oldest stars we know of are sometimes called population 2 stars, or simply old population stars. They formed in the early universe when the only elements available were hydrogen and helium, with just traces of lithium, the 3 lightest elements created in the Big Bang itself. These stars contain almost no heavier elements, what astronomers call metals, not because the terminology is very chemical, but because in astronomical convention, any element heavier than helium is called a metal. Our Sun, by contrast, is a population 1 star, a younger star that formed from gas already enriched by previous generations. It contains a greater abundance of heavier elements, elements that only exist because earlier stars created them and then scattered them into space when they died. The galaxy, then, has a kind of generational depth to it. There are stars alive today that formed in the very early universe, burning steadily and slowly through their long lives. And there are stars like our Sun, 2nd or 3rd generation stars, formed from the enriched debris of stellar ancestors long since gone. There are stars forming right now, this very moment, in molecular clouds throughout the galaxy that will still be burning long after our Sun has ended its life 5 billion years from now. The galaxy is, in this sense, a multi-generational story. Not a single moment or a single event, but a long, continuous narrative of birth and death and transformation and renewal, playing out across timescales that make even the whole of human history seem like a brief, bright moment. Human civilization has existed for perhaps 10,000 years. The Milky Way has been here for 13 billion. Our entire civilization occupies less than 1/1,000,000th of the galaxy's lifespan. Not so that we feel insignificant, but so that we might feel, perhaps, the way you feel when you stand in a very old forest. The trees have been there much longer than you have. They will be there long after you are gone. And yet, you are there among them for a while, breathing the air they have cleaned, sheltered by their presence, part of the same world they inhabit. We are young in galactic terms. The universe was already more than 9 billion years old when our solar system formed. By then, countless generations of stars had already lived their entire lives. Elements had been created and scattered and gathered and rescattered and gathered again. The galactic disk had been rotating for billions of years. Spiral arms had wound and wound again. And then, in one particular cloud of gas and dust, in one particular region of one particular arm, gravity began gathering material toward a new sun. That was our beginning. We are the universe becoming aware of itself at a particular point in time, in a particular location, through a particular form of awareness. The atoms that make up your body are ancient. They were forged in stars that died before the sun was born. They have been part of nebulae, part of asteroids, part of the early Earth, part of the ocean, part of single-celled organisms, part of the long, unbroken chain of life on this planet. And now, for a brief time, they are arranged in the pattern that is you. That is not a small thing. It is, in fact, one of the most extraordinary things that we know of. We tend to think of the Earth as stationary. We feel it beneath us, solid and still. When we go to bed at night, we expect to wake up in the same place we fell asleep. And in the most practical sense, that is true. But the Earth is, in fact, in constant, multiple kinds of motions simultaneously. The Earth rotates on its axis once every 24 hours. This rotation is what gives us the cycle of day and night. At the equator, this rotation carries you through space at roughly 1,600 kilometers per hour. Right now, as you read or listen to this, you are moving at 1,600 kilometers per hour depending on where you are on Earth, simply because the planet is spinning. The Earth also orbits the Sun. It completes one full orbit in about 365 days, which is, of course, our year. To cover the enormous circumference of its orbit around the Sun in that time, the Earth must travel at about 30 kilometers per second. That is 30 kilometers every second. A bullet from a rifle travels at about 1 kilometer per second. The Earth moves through space 30 times faster than that, continuously, without pause. The Sun, carrying the Earth and all the other planets with it, is also moving through the galaxy. The Sun orbits the center of the Milky Way. It takes the Sun and us along with it approximately 220 to 250 million years to complete one full orbit around the galactic center. Astronomers sometimes call this period a cosmic year or a galactic year. Our Sun has completed roughly 18 to 20 galactic years in its lifetime. When our Sun was born, the universe had just completed its first 40-some galactic years. Since life first emerged on Earth, the solar system has made about 4 complete trips around the galaxy. The speed at which the solar system moves in its galactic orbit is approximately 230 kilometers per second. 230 kilometers every second, curving slowly around the galactic center in a vast, gentle arc. And even beyond that, the Milky Way itself is moving. The Milky Way is part of a small group of galaxies called the Local Group. The Local Group contains about 50 or so galaxies, most of them small dwarf galaxies, with the two largest being the Milky Way and the Andromeda Galaxy. These galaxies are gravitationally bound to each other, which means they move around their common center of mass. The Local Group itself is part of a larger structure called the Virgo supercluster, which is part of an even larger structure called the Laniakea supercluster. Laniakea means immeasurable heaven in Hawaiian, which is perhaps the most beautifully appropriate name that could have been given to it. The Laniakea supercluster contains perhaps 100,000 galaxies and stretches across 500 million light-years of space. And the Milky Way, along with everything in the Local Group, is drifting slowly within Laniakea, moving in the direction of the supercluster's gravitational center, a region of extraordinary mass concentration called the Great Attractor. The Great Attractor is a mysterious region of space that sits in the direction of the constellation Norma, behind the dense star fields and dust of the Milky Way's own disk. For a long time, astronomers knew the Great Attractor existed because of the way it was pulling on galaxies in its vicinity, but could not see it directly because the disk of our own galaxy was in the way. It was like knowing something enormous is just beyond a wall without being able to see over the wall. More recent observations using X-ray and radio wavelengths that can penetrate the galactic disk have allowed astronomers to peer through and confirm that the Great Attractor region is indeed a massive concentration of clusters of galaxies, gravitationally pulling on everything in a large region of the universe, including us, at a speed of about 600 kilometers per second. So to summarize our motion, we are spinning on the Earth's axis, orbiting the Sun, traveling with the solar system through the Milky Way's disk, orbiting the galactic center, moving with the Milky Way through the Local Group, drifting within Laniakea towards the Great Attractor, and moving with the expansion of the universe itself. All of this motion, all of these layers of movement, and yet, here you are, perfectly still. Or at least, you feel still. The body has no instruments to detect any of these motions directly. We move through space at hundreds of kilometers per second and feel none of it. There is something almost meditative in that. The universe moves on its own vast terms, in its own vast ways, and we sit quietly within it, apparently still, apparently at rest, breathing slowly in and out, feeling the solid ground beneath us. The stillness we feel is real, in its way. It is the stillness of being carried, not the stillness of not moving. We are passengers in something enormous, borne along on the currents of gravity and cosmic expansion, sitting as quietly as a leaf on a river. There is more to the Milky Way than meets the eye. Far more, in fact. When astronomers look at the Milky Way and try to understand it completely, they discover something puzzling. The visible galaxy, the disk of stars and gas and dust and the central bulge, the things that actually emit or reflect light and can therefore be seen, accounts for only a fraction of the total mass of the galaxy. The rest of the mass, the large majority of it, is in a form that astronomers call dark matter. Dark matter is one of the great quiet mysteries of modern science. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation of any kind that we have been able to detect. It cannot be seen directly, not with optical telescopes, not with radio telescopes, not with X-ray or infrared or ultraviolet instruments. What dark matter does do is interact gravitationally. It has mass, and therefore it pulls on other things through gravity. Astronomers know it exists because of the effects of that gravitational pull on the things they can see. The most elegant evidence for dark matter in galaxies like the Milky Way comes from studying how fast different parts of a galaxy rotate. If a galaxy contained only the mass that can be seen, you would expect the outer parts of the galaxy to rotate more slowly than the inner parts, the same way the outer planets in our solar system move more slowly in their orbits than their inner ones. This makes intuitive sense. The further you are from the center of a gravitational system, the weaker the pull, and the slower you need to move to maintain your orbit. But when astronomers actually measure the rotation speeds of galaxies, they find something different. The outer parts of galaxies rotate at nearly the same speed as the inner parts. The rotation curve, as it is called, stays roughly flat, where it should be declining. The only way to explain this flat rotation curve is to assume that there is additional mass present that we cannot see, mass spread throughout and around the galaxy in a kind of spherical halo. This invisible halo of mass, if it exists, would provide the additional gravitational pull needed to keep the outer stars moving at the speeds we observe. This is the dark matter halo. It surrounds the visible disk of the Milky Way in all directions, extending outward far beyond the disk itself, perhaps hundreds of thousands of light years in every direction. It is not concentrated in the disk. It forms a roughly spherical cloud, enormous and invisible, within which the bright visible galaxy rotates. The dark matter halo of the Milky Way is thought to contain several times as much mass as all the visible stars and gas combined. Perhaps as much as 80 to 90% of the total mass of the galaxy might be in the form of dark matter. We do not know what dark matter is made of. That is perhaps the most honest thing that can be said about it. Numerous candidates have been proposed and studied over the years, ranging from exotic subatomic particles called WIMPs, weakly interacting massive particles, to hypothetical particles called axions, to various other possibilities. None have been directly detected yet, despite decades of careful searching with increasingly sensitive instruments. There are also alternative theories that suggest dark matter might not be a type of particle at all, that the flat rotation curves might be explained instead by modifications to our understanding of gravity at large scales. These modified gravity theories are taken seriously by a minority of researchers and continue to be investigated. The honest position is that the universe contains something, accounting for the large majority of the mass of galaxies like ours, that we do not yet understand. In science, that is not a failure. It is an invitation. The dark matter halo, Whatever it is made of is all around us right now. It is moving through this room, through your body, through the earth itself, an invisible presence everywhere and nowhere visible, passing through matter without interacting in any way we can detect. There is something strangely calming about that. The universe is larger and more complex than what can be seen. Most of it, in terms of mass, is hidden from us. We are embedded in something we cannot fully observe or understand, something enormous and all-pervading that nevertheless carries us gently through space without any apparent consequence for us directly. The visible galaxy, the one we can see and map and study, is like the surface of the ocean. Beneath it, or rather surrounding it in all directions, is something vast and dark and quiet, the halo within which the visible structure lives and moves. Beyond the dark matter halo, there is also a region called the stellar halo. This is a more diffuse region surrounding the disk of the galaxy, containing old stars, globular clusters, streams of stars torn from disrupted dwarf galaxies, and wisps of ancient material that have been orbiting the galaxy for billions of years. The stellar halo is sparse compared to the disk, but it is there, a kind of outer atmosphere of the galaxy, quiet and ancient and far-flung. Globular clusters are among the most beautiful objects in the galaxy. They are tightly packed spherical clusters of hundreds of thousands of stars, held together by gravity, orbiting the galaxy in great sweeping elliptical paths. The Milky Way has perhaps 150 to 200 known globular clusters. When seen through a telescope, they look like soft spherical clouds of light that resolve at higher magnification into individual stars packed together in extraordinary density. The stars in globular clusters are among the oldest in the galaxy. They formed very early, some of them 13 billion years ago, and have been orbiting the galaxy ever since, slowly sweeping through their long, looping paths, outlasting entire generations of disk stars. There is something deeply peaceful about them, these ancient spherical cities of stars, floating in the outer reaches of the galaxy, persisting long and quietly through the vast sweep of cosmic time. The Milky Way has a neighbor. In the direction of the constellation Andromeda, at a distance of about 2.5 million light-years, there is another galaxy roughly similar in size to our own. It is called the Andromeda Galaxy, or sometimes Messier 31, from its number in the Messier catalogue of deep sky objects. On a very dark, clear night, it is just barely visible to the naked eye as a faint, small smudge of light, the most distant thing human eyes can see without optical aid. That faint smudge is an entire galaxy containing perhaps 1 trillion stars. The Andromeda Galaxy and the Milky Way are, by the standards of the universe, close to each other. They are both members of the local group, and their mutual gravitational attraction has been drawing them together for a very long time. Astronomers have determined that the Andromeda Galaxy is approaching the Milky Way at a speed of roughly 110 kilometers per second. That sounds fast in human terms. But at a current distance of 2.5 million light-years, it means the two galaxies will not come close to merging for approximately 4.5 billion years. 4.5 billion years from now. This is approximately the same age as our solar system is today. So in a sense, the merger of the Milky Way and Andromeda is as far in our future as the formation of the solar system is in our past. It is a very long time away. When the two galaxies do eventually come together, the event will unfold slowly, over hundreds of millions of years. Galaxies are mostly empty space. Despite containing hundreds of billions of stars each, the stars themselves are so small relative to the distances between them that direct collisions between individual stars are extremely unlikely. The galaxies will interpenetrate and distort and fold into each other gravitationally, without most of the stars actually hitting anything. The shapes of both galaxies will be disturbed. Great tidal tails of stars will be flung outward. New waves of star formation will be triggered as the gas clouds of both galaxies collide and compress. The two central black holes, Sagittarius A star and its counterpart in Andromeda, will slowly spiral toward each other over millions of years and eventually merge into one larger black hole. The result, after all of this slow gravitational choreography plays out, will be a single, larger galaxy. Astronomers have already given this future galaxy a name. They sometimes call it Milky Way, a blend of Milky Way and Andromeda. Milky Way will not look like either of its parents. The merger process tends to produce a different type of galaxy altogether. Instead of the elegant spiral structure both the Milky Way and Andromeda have today, the merged galaxy will likely become an elliptical galaxy, a rounder, smoother, less structured type of galaxy without obvious spiral arms. Elliptical galaxies are in some ways the quiet elders of the galaxy world. They tend to be older with less active star formation than spirals. They have used up much of their gas in previous rounds of star formation or expelled it during mergers. They glow softly with the light of their older, redder stars. It is worth noting that this future merger does not mean the end of our solar system or of life on Earth, assuming life continues here that long. As mentioned, direct star collisions are extremely unlikely. Our Sun and its planets will most likely survive the merger intact, simply finding themselves in a different galactic environment afterward, perhaps with a different view of the night sky, but otherwise continuing on their long, slow journey. The night sky on a future Earth during the early stages of the merger, perhaps 3 or 4 billion years from now, would be extraordinary. Andromeda, currently a faint smudge, will have grown large and bright in the sky, a sprawling, beautiful structure stretching across a large portion of the visible sky, much larger than the full moon appears today. The two galaxies will slowly distort each other, and over millions of years the shapes will change and evolve in ways that would be remarkable to witness if anything were there to witness them. But this is all so far in the future that it is more like a distant dream than a concern. The Sun will not begin to significantly change its character for another 5 billion years or so. The merger with Andromeda begins in about 4.5 billion years. These timescales are beyond all practical consequence for anything alive today. They are simply part of the long, unhurried story of the universe. The Milky Way has already had mergers before. The halo of the galaxy, with its streams of stars and disrupted globular clusters, bears the traces of past encounters. Small dwarf galaxies have been absorbed into the Milky Way over billions of years. Their stars are now scattered through our galaxy's halo, assimilated into the larger structure, still orbiting but no longer part of any recognizable separate galaxy. The Milky Way grows slowly over billions of years by absorbing smaller neighbors. It is the nature of large galaxies in the universe to grow through mergers and accretion over the long sweep of cosmic time. And on an even longer timescale, the universe itself continues to expand. The space between galaxy clusters is growing, stretched by the expansion of the universe. In the very far future, billions and trillions of years from now, distant galaxy clusters will have receded so far from us that they will be invisible, beyond the observable horizon. The universe will become a lonelier and darker place over vast timescales. But that is extraordinarily far away in time. For now, and for all of the time that is meaningful in human terms, and for all of the time that is meaningful in the terms of life on Earth, the universe is as it is. Vast, full of galaxies, ancient, continuing. We have traveled a long way together tonight. From the quiet field where we lay and looked up at the night sky, through the gentle band of starlight that is our view of the Milky Way from within it. Past the details of where we are in our comfortable suburban address in the Orion Arm, 2/3 of the way out from the galactic center. We considered the size of the galaxy, something like 100,000 light-years across, containing 100 to 400 billion stars, most of them with their own systems of planets. We followed the curve of the spiral arms, those slow density waves that compress gas into new stars as they move through the disk. We looked gently towards the galactic center and the supermassive black hole that sits there, steady and ancient, 4 million solar masses, generating its soft ring of glowing gas, 26,000 light-years away, exerting no particular influence on our peaceful address in the galaxy. We spent time in the nebulae, those enormous clouds of gas and dust where stars are slowly, patiently born, and we acknowledged that the atoms in our own bodies once passed through stellar furnaces, that we are, in a literal sense, made of ancient starlight. We sat with the age of the galaxy, 13 billion years and counting, and felt perhaps some perspective on the brief, bright moment that is a human life, not diminishment, but scale. The way standing beside an old tree gives you a feeling not of smallness, but of belonging to something continuous. We moved through space together, carried at hundreds of kilometers per second in multiple directions simultaneously, yet feeling perfectly still, perfectly at rest, passengers in something enormous. We acknowledged the dark matter halo, that invisible presence everywhere around us, and found in its mystery not anxiety but invitation, the gentle reminder that the universe is larger and stranger and more interesting than what can be seen. And we looked gently toward the future, toward the eventual slow embrace of Andromeda 4.5 billion years from now, and found it to be nothing frightening, only a distant change in an endlessly changing universe, as natural as the seasons, simply on a much longer clock. Now let us come back to where we began. You are here. You are on a small, warm planet circling a medium-sized star in the Orion arm of a spiral galaxy, in the local group, in the Laniakea supercluster, in a universe 13.5 billion years old that contains more galaxies than there are grains of sand on all the beaches of Earth. And you are here, right now, in this moment, breathing slowly. The Milky Way is above you right now, whether you can see it or not. It does not go away when clouds cover the sky. It does not disappear when city lights wash it out. It is always there, that slow, turning river of 250 billion stars, going about the ancient, patient business of existing. You are part of it. Not just beneath it or near it or inside it, but made of the same material, subject to the same gravity, participating in the same slow cosmic story. Your atoms are as old as the universe. Some of the hydrogen in your body was created in the first 3 minutes after the Big Bang. It has been traveling through space and time ever since, assembling and disassembling into different forms, flowing through nebulae and stars and asteroids and planets and oceans and single cells, and every ancestor you have ever had. And now, it is here briefly, arranged into the specific pattern that is you. That is worth sitting with for a moment. Not thinking about, necessarily, just sitting with. The galaxy does not hurry. It has time. It has billions of years more to continue its slow, spiraling existence. The stars burning tonight have been burning for billions of years and will continue for billions more. The great dark halo surrounds it all, quiet and invisible and vast. None of what is pressing on you today exists at that scale. The worries, the tasks undone, the things you are uncertain about. All of it is very, very small against the backdrop of 400 billion stars and 13 billion years. That is not meant to make those things feel unimportant. What you feel and experience and carry matters. But sometimes the mind needs to be reminded of scale. Sometimes it helps to look up, or to imagine looking up, and feel the size of the thing you are sitting inside. To remember that you are not required to understand all of it, that it will continue whether you are resting or not, that the universe has never asked anything of you except to exist within it, which you are already doing right now, without any effort at all. Tonight, if you have the chance, step outside. Look up. Even if you are in a city and can see only a handful of stars through the light pollution, they are there, each one a sun, many with planets, some perhaps with something looking back. And if you are somewhere dark enough to see the pale band of the Milky Way stretching across the sky, take a moment with it. Let your eyes soften and rest on it. That blur of light is 250 billion stars. So far away they merge into a single, gentle glow. You are inside that glow. You have always been inside it. You always will be. Rest now. The galaxy will be there when you wake. It always is. This has been Quiet Knowledge. Thank you for spending this time with the Milky Way. Stars come in a remarkable range of sizes, temperatures, and colors. Our Sun is a yellow dwarf star, which astronomers classify as a G-type main sequence star. It sits comfortably in the middle of the range of stellar sizes and temperatures. It is not particularly large or particularly small, not notably hot or notably cool by stellar standards. It is, in the best possible sense, an ordinary star. And this ordinariness turns out to be important. Very large stars, called giant and supergiant stars, burn through their fuel extremely rapidly. A star 10 times the mass of the Sun might live for only 20 to 30 million years before dying in a supernova. That sounds like a long time, but in the context of the time it takes for complex life to evolve on a planet, it is very short. Life on Earth took billions of years to develop, from simple, single-celled organisms to complex animals. If the Sun had burned out in 20 million years, life would not have had time to develop beyond the most primitive forms. Our Sun, by contrast, is expected to continue burning comfortably for about another 5 billion years, giving us a total lifespan of about 10 billion years. This long, steady life is one of the conditions that has allowed complex life to develop on Earth. At the other end of the scale, there are red dwarf stars, which are much smaller and cooler than our Sun. Red dwarfs burn their fuel so slowly and so frugally that some of them are expected to live for trillions of years, far longer than the current age of the universe. A red dwarf star alive today will still be burning long after the last stars of our Sun's type have gone cold. The Milky Way is full of red dwarfs. They are by far the most common type of star in the galaxy. Estimates suggest that somewhere around 70 to 80% of all stars are red dwarfs. Our nearest stellar neighbor, Proxima Centauri, is a red dwarf. At roughly 12% the mass of the Sun, it burns so slowly that it will remain on the main sequence for several trillion years. These long-lived, quiet little stars are currently in the early phase of their lives. The universe has not existed long enough for any red dwarf to have completed its full lifespan. They are all still burning, still fusing hydrogen, still providing warmth to any planets that orbit them. The diversity of stars is something that bears gentle contemplation. White-hot O-type giants burning fierce and blue-white for a few million years. Steady yellow G-type stars like our Sun, burning for 10 billion years. Cool orange K-type stars, somewhat smaller than the Sun, burning for 15 to 30 billion years. Tiny red M-type dwarfs, burning for trillions of years in their gentle, frugal way. Each of these types of stars has its own character, its own light, its own place in the story of the galaxy. And many of them, the quieter and longer-lived ones especially, are surrounded by planets, some of which orbit in the zones where liquid water might exist, where the conditions for life as we understand it might be present. The Milky Way may contain hundreds of billions of planets. That number comes from the work of the Kepler Space Telescope and subsequent missions that have detected planets orbiting distant stars by measuring the tiny dimming of starlight that occurs when a planet passes in front of its star. From these observations, astronomers have determined that most stars have at least one planet, and many have several. If the galaxy has 200 billion stars and most of them have planets, the total number of planets is enormous. Many of these planets will be gas giants or ice giants, large worlds without solid surfaces. But a significant fraction will be rocky, Earth-sized worlds, orbiting at distances where temperatures might allow liquid water. Whether any of those planets have life is something we do not yet know. It is one of the most profound open questions in science, perhaps in all of human thought. We are a form of life that has become aware of the universe it exists within, and we look out at hundreds of billions of other star systems and wonder if anything else looks back. We do not know the answer. We may be one of many, perhaps countless others. We may be rare, perhaps the only ones within a very large region. The search for signs of life beyond Earth continues, using radio telescopes and spectrum analysis of planetary atmospheres and direct imaging of exoplanets. So far, in all our listening and looking, we have not found a clear signal. But the search is young, the galaxy is large, and the number of candidate worlds is vast. Whatever the answer turns out to be, there is something quietly moving about the fact that we look. There is one more thing about the night sky that is worth sitting with slowly. When you look at a star, you are not seeing the star as it is now. You are seeing the star as it was when the light that is reaching your eye left it. Light travels very fast, but it does not travel instantly. The light from the sun takes about 8 minutes to reach us. When you look at the sun, you are seeing it as it was 8 minutes ago. The light from the moon takes about 1 1/3 seconds. When you look at the moon, you are seeing it as it was a little over a second ago. But the stars are much, much farther away. The nearest star beyond the Sun, Proxima Centauri, is about 4 light years away. When you look at it, you are seeing light that left it 4 years ago. The star Sirius, the brightest star in the night sky, is about 8.5 light years away. The light reaching your eyes from Sirius tonight left that star 8.5 years ago. And stars further away carry even older light. The Pleiades cluster, that soft grouping of stars visible in the constellation Taurus, is about 400 light years away. The light from those stars left 400 years ago. When Galileo first turned his telescope on them, the light he saw had left the Pleiades when the telescope had not yet been invented. And the pale band of the Milky Way itself, that soft glow across the sky, is made of light that traveled for thousands or tens of thousands of years to reach your eye. Some of the light in that band started its journey when the last ice age was still ending, when glaciers still covered much of the northern continents, when the ancestors of the world's great civilizations were just beginning to develop agriculture. The night sky is not a single moment. It is a layered display of different times. When you look up, you look back. Every star you see is a different distance away, carrying light from a different moment in the past. The sky is a kind of time map, a simultaneous display of thousands of different historical moments, all arriving at your retina in the same instant, the now of yore, perception flattening all of those deep times into a single present. Some of the stars you can see tonight might not exist anymore. The light from a star 1,000 light years away left it 1,000 years ago. In the time that light has been traveling toward you, the star might have aged significantly or even ended its life. You would not know yet. The news travels at the speed of light, and the news has not arrived. You are receiving messages from the past. That is what stargazing is. It is a form of receiving. You are not doing anything to the sky by looking at it. You are simply receiving the light that has been traveling toward you, in some cases for a very long time, and allowing it to reach you. There is something in that image that is worth carrying with you. The universe has been sending its light in all directions, in every moment, for 13 billion years. Some of that light, a tiny fraction of the total, has been traveling along paths that end at your eyes. Tonight, in this moment, you are the destination of light that has been traveling for a very long time. We have talked much about the stars themselves, their types and their sizes and their births and their long lives. But most of the galaxy, by volume, is not stars. Most of the galaxy is space. The space between stars is not empty in the way that everyday language suggests when it uses the word empty. There is material between the stars, what astronomers call the interstellar medium. This material includes hydrogen gas in various forms, from cold, dense molecular hydrogen in the centers of giant molecular clouds, to warm atomic hydrogen in more diffuse regions, to hot ionized hydrogen in regions around young, energetic stars. It includes helium, it includes dust, tiny solid particles of silicates and carbonaceous material, sometimes coated in ice. It includes complex molecules, including organic molecules, the building blocks of chemistry that we associate with life. But for all that, it is extraordinarily thin. The average density of the interstellar medium in a region like ours is roughly 1 atom per cubic centimeter. A cubic centimeter is about the size of a sugar cube. In a typical sugar cube-sized volume of the space between the stars, there is, on average, 1 single atom. By comparison, the air you are breathing right now contains about 27 million trillion molecules per cubic centimeter. The interstellar medium is not nothing, but it is so thin as to be, for all practical purposes, an extraordinary emptiness. If you could remove all of the stars from the galaxy and leave only the interstellar medium, the result would be almost completely invisible. A ghost of material spread through an enormous volume, too thin to interact with, almost too thin to measure. The galaxy is mostly space. And within that space, the stars are separated by vast distances. The distance from our Sun to the nearest star, Proxima Centauri, is about 40 trillion kilometers. If the Sun were the size of a grapefruit, sitting on a table, Proxima Centauri would be represented by another grapefruit, sitting about 4,200 kilometers away. That is about the distance from New York to Berlin. 2 grapefruits separated by the distance from New York to Berlin, with essentially nothing between them. That is the scale of the space between even the nearest stars. And yet, from a great distance, from the position of a galaxy in the Virgo supercluster looking at the Milky Way, that vast star-speckled space would look like a solid, glowing disk. Scale does that. What is nearly entirely empty at one scale looks solid and luminous at another. The way a forest looks from an airplane like a solid green carpet, even though, if you were standing in it, you would see mostly air and space between the individual trees. The galaxy is a pattern that emerges from vast distances. Up close, it is mostly space, with stars here and there, separated by distances almost too great to comprehend. From far away, all of that space resolves into a coherent, beautiful structure, a glowing disk with spiral arms and a bright center. Perspective does not change the truth of things, but it does change what is visible. What looks like emptiness at one scale looks like fullness at another. Perhaps there is something in that worth thinking about softly as you rest. The Milky Way is, in a sense, a living system. Not living in the biological sense, not conscious or intentional, but in the sense that it takes in material and transforms it and puts it back out in changed form, that it cycles its ingredients through processes of birth and death and renewal. There is something that rhymes with living in the way the galaxy operates. Stars are born from clouds of gas and dust. Over their long lives, they fuse lighter elements into heavier ones in their cores. When they die, they return that material, now enriched with the heavier elements they have created, to the interstellar medium. That enriched gas drifts and mixes and slowly accumulates in molecular clouds. In those clouds, gravity begins to gather it again, and new stars form, stars enriched in metals, stars that can now build rocky planets with complex chemistry. This is the galaxy's long, slow metabolism. Each generation of stars enriches the next. The first stars in the universe, born from only hydrogen and helium, could not have formed rocky planets. There were no heavier elements. They burned and died and seeded the galaxy with carbon and oxygen and nitrogen and magnesium and silicon and iron. The next generation of stars had these materials available and could form more complex planetary systems. And so on, generation after generation, the galaxy's inventory of heavy elements has slowly grown richer, making more elaborate chemistry, more complex planets, more diverse conditions possible over time. We are the beneficiaries of this long enrichment process. Our Sun, formed 4.5 billion years ago, had access to heavy elements created by multiple previous generations of stellar evolution. The Earth, formed from the same enriched cloud, was able to develop the complex chemistry that eventually gave rise to living things. If you had been born in the very early universe from a first-generation star system, there would have been no carbon, no oxygen, no silicon, no iron. The chemistry of life as we know it would have been impossible. We exist in a specific cosmic time, late enough in the galaxy's history that the stellar metallicity has reached the level needed for the kind of chemistry life requires. Another reason our time and place turn out to be, in every measurable way, quite fortunate. The galaxy will continue its slow metabolism. New stars will form in the molecular clouds that still have plenty of gas. Old stars will die, some quietly, some violently, returning their enriched material to the interstellar medium. The spiral arms will continue their slow sweeping through the disk. The central black hole will sit steady at the core, occasionally consuming a small amount of gas, mostly quiet. The whole vast system, 250 billion stars, 1 trillion solar masses, 100,000 light-years across, will continue to do what it does, with or without any observation, with or without any understanding, as patient and indifferent and steady as a river. We are, for the moment, observers. We are the part of the galaxy that has developed the capacity to look back at the whole, to marvel at it, to try to understand it. That capacity is very new. Anatomically, modern humans have existed for about 300,000 years. Systematic astronomy has existed for only a few thousand. The understanding of the galaxy as a structure containing hundreds of billions of stars has existed for barely a century. The imaging of a black hole happened in 2019, barely a handful of years ago. In 13 billion years of galactic history, the moment at which the galaxy became aware of itself through the medium of human consciousness is very recent indeed. We arrived late to the story, but we arrived, and we have been looking up ever since. If you ever have the opportunity to look through a telescope at a globular cluster, take it. Point the instrument at one of the Milky Way's great spherical gatherings of ancient stars and allow your eye to adjust. And what you will see is something that is difficult to describe without sounding like you are reaching for poetry when you mean to be describing science. You will see a soft ball of light that, as the eye and the telescope work together, begins to resolve at the edges into individual stars, packed together so densely near the center that they blur again into a collective glow. Hundreds of thousands of stars, each one of them ancient, many of them older than our sun by several billion years, gathered into a sphere and orbiting the galaxy in a long, slow, sweeping path. The globular cluster called Omega Centauri is the largest and most massive globular cluster associated with the Milky Way. It is visible from the southern hemisphere as a faint smudge to the naked eye, but through a telescope it opens into something extraordinary. Perhaps 10 million stars packed into a region about 150 light-years across. All of them old, many of them billions of years older than the solar system. Omega Centauri is thought by many astronomers to be the stripped core of a small galaxy that was captured and absorbed by the Milky Way long ago. Its unusual characteristics, including a range of stellar ages and a possible central black hole, suggest a more complex origin than a simple globular cluster. It may be all that remains of an entire small galaxy, its outer stars stripped away by the tidal forces of the Milky Way, leaving only the dense inner core, still orbiting, still coherent after billions of years. There is something almost tender about that image. A small galaxy, captured by a larger one, losing its outer reaches over billions of years, but its heart persisting, still here, still turning, still a structure even after everything else has been taken. The Milky Way has approximately 150 to 200 known globular clusters. Each of them is a separate world of ancient stars, orbiting in the halo of the galaxy in their own independent paths. Some of them come close to the galactic disk and swing out again into the halo in long, looping orbits that take hundreds of millions of years to complete. If you were a hypothetical observer on a planet orbiting a star in a dense globular cluster near the galactic center, the night sky would look very different from ours. Instead of a dark sky with scattered stars, the sky would be bright with the combined light of thousands of nearby stars. At the heart of the densest clusters, the night might be nearly as bright as a full moon night on Earth. Lit not by a single moon, but by the collective glow of countless neighboring stars. Our sky, by comparison, is wonderfully dark. We live in a quiet neighborhood, and our nights are genuinely dark, genuinely suited to rest and stillness, and the gentle contemplation of distant things. That darkness is itself a gift. There is a name for the idea that the night sky is dark, rather than uniformly bright. It is called Olbers' paradox, named after a 19th century astronomer who pointed out a puzzling logical problem. If the universe were infinite and uniformly filled with stars, every line of sight from Earth should eventually end at a star. The entire sky should be as bright as the surface of a typical star, blazing in every direction. The resolution of Olbers' paradox came with the understanding that the universe has a finite age. It has only existed for about 13.8 billion years. Light from stars further than 13.8 billion light-years has not had time to reach us, yet. Additionally, the expansion of the universe stretches and reddens the light from very distant sources, making them less energetic. The combined result is a night sky that is dark, punctuated by the light of stars and galaxies, close enough for their light to have reached us in the age of the universe. The darkness of the night sky, then, is not simply absence, it is a sign of the age of the universe. It is the darkness that results from a cosmos of finite age. Every dark patch of sky between the stars is a window into a region from which the light of distant stars has not yet arrived. The darkness is full of meaning. And it is restful. Across human history and across all human cultures, the night sky has been a source of meaning and story and orientation. Long before the scientific understanding of what the stars actually are, people looked up at the night sky and saw patterns. They named those patterns, grouped the stars into pictures of animals and heroes and gods and tools and everyday objects. They used those patterns to navigate, to track the seasons, to mark the passage of time, to anchor the stories of their cultures. In the Marshall Islands, traditional navigators used the stars to guide open ocean voyages between islands separated by hundreds of kilometers of open Pacific, carrying in their minds detailed knowledge of which stars rose and set over which islands, how the swells of the ocean moved under their canoes, how the behavior of birds and the color of the water changed as land approached. In the Polynesian tradition of wayfinding that allowed people to colonize the remotest islands of the Pacific, navigators memorized the paths of stars across the sky throughout the year and used them with a precision that navigators using only instruments would have difficulty matching. The stars were not decoration, they were infrastructure. In ancient Egypt, the construction of temples and pyramids was aligned with remarkable precision to celestial events. The rising of particular stars, the movement of the sun, the flooding of the Nile predicted by the heliacal rising of Sirius, when it first appeared above the horizon just before dawn after a period of invisibility. The sky was woven into the practical and ceremonial life of the culture. Indigenous Australian astronomical traditions are among the oldest continuous astronomical knowledge systems in the world. The dark constellations of the Milky Way, the shapes formed not by groupings of stars but by the dark patches of dust that obscure the star-rich regions of the galactic disk, are as meaningful in these traditions as the bright star patterns of the Western zodiac. The Emu in the Sky, a constellation traced through dark nebulae along the Milky Way, rises at the time of year when emus are laying their eggs. This is ecological knowledge encoded in the night sky, astronomy in the service of life. The Navajo people of the American Southwest have their own rich astronomical tradition in which the stars are part of a complex cosmological framework. The Pleiades cluster, visible in the constellation Taurus, marks in many cultures around the world the division of the year, the time of planting or harvest, the time of gathering or dispersal. The same cluster of stars, visible from every part of the Earth, has been given names and meanings and stories by cultures on every continent. It appears in ancient Greek myth, in the Vedic traditions of India, in Chinese astronomical records, in the oral traditions of indigenous peoples of the Americas and Africa and Australia. The night sky is the one thing that all human beings throughout all of history have had in common. Every person who has ever lived has looked up at the same stars. The stars themselves have changed imperceptibly over the span of human civilization, so gradually that the sky Paleolithic hunters saw 30,000 years ago is essentially the sky we see tonight. There is a continuity in that which is difficult to fully feel but worth attempting. The same Milky Way that arched over the first humans to look up and wonder about it, arches over you tonight. The light, reaching your eyes from the more distant stars, left those stars long before our species existed. The sky is ancient in a way that nothing else in our daily experience approaches. And yet, it is also intimate. It is the sky above your home, your neighborhood, your life. It changes with the seasons in a predictable, comforting way. The same stars that rose in autumn when you were a child will rise in autumn for the rest of your life. The patterns are stable, the rhythms reliable, the sky a constant in a life full of change. People who have lived through great difficulty often speak of the night sky as a source of consolation. The philosopher Immanuel Kant wrote that two things filled him with ever-increasing wonder and awe: the starry sky above him and the moral law within him. The connection between looking up at the vast, impersonal sky and finding within oneself something personal and meaningful is not accidental. The sky gives scale, and scale gently received can be a form of rest. When everything feels important and urgent and pressing, the sky quietly reminds you that there is a much larger context. Not to dismiss your concerns, but to hold them in a wider frame. Not to make you feel small, but to make the universe feel present, companionable, vast, beyond any problem. The Milky Way has been a companion to human beings for as long as human beings have existed. It predates our species. It will outlast it. But for this particular window of time, it is the sky above the beings who have become capable of understanding what it is, and the knowledge and the wonder seem, if anything, to add to, rather than diminish the simple pleasure of looking up. We have spent some time with the past and present of the Milky Way. Let us spend a little time, gently and without urgency, with its future, not the eventual merger with Andromeda, which we have already visited. Something longer, something quieter. The universe is thought to be heading on very long timescales toward a state of increasing stillness. In the current era, the universe is active and energetic. Galaxies are forming stars. Stars are burning. Supernovae are exploding. Pulsars are spinning. Quasars are blazing. The universe, viewed on large scales, is full of events. But the universe is also running down, in a sense. The raw material for star formation is finite. There is only so much gas. As stars form and burn and die, they lock away some mass in the remnants they leave behind: white dwarfs and neutron stars and black holes. This mass is no longer available for new star formation. Over time, the rate of star formation in the universe has been declining. It peaked about 10 billion years ago and has been gradually decreasing since. The galaxy will continue forming new stars for a very long time, but the pace will slowly, gradually decrease as the available gas is used up. Eventually, many billions of years from now, the gas will be mostly gone, and star formation will slow to a halt. The last stars to form and burn in the galaxy will be red dwarfs, those small, frugal, long-lived stars that burn their fuel so slowly they can last for trillions of years. The last generation of stars in the universe will be dim, cool, and red, glowing faintly in the dark. After those last red dwarfs finally cool and go dark, the stellar remnants will remain, white dwarfs slowly cooling over trillions of years into cold, dark objects called black dwarfs, neutron stars, black holes, and the dark matter halo still there, still gravitationally present, even as everything it once contained has gone cold and dark. This is called the degenerate era, and then the black hole era, in the speculative cosmology of the very long-term future. But these eras are so enormously far in the future, trillions and quadrillions of years from now, that they have no bearing on anything living today. What is worth knowing is this: we are alive at a very particular moment in cosmic history. We are in the stelliferous era, the age of stars. The universe is currently producing light and heat at a rate that makes it hospitable to life as we understand it. This era will last for trillions of years in total, but we are currently somewhere in the earlier part of it. Stars are still forming. The universe is still warm and bright and full of energy. Life, wherever it exists, has the light and heat it needs. It is a good era to be alive in. The Milky Way, in this current era, is producing new stars and will continue to do so. It is not declining. It is not dying. It is simply at a different phase of its long life than it was in the early universe, when the star formation was more frantic and intense. The galaxy is older and a little calmer than it once was. Something like middle age, perhaps, if you can apply such a concept to an entity that will continue for trillions of years, settled into its patterns, still creative, still generating new suns, but more measured than in the intense early phase of its youth. There is something recognizable in that arc. Even if the timescales are incomprehensibly large, the universe itself seems to have a kind of life history. An energetic beginning, a long, productive middle period, and an eventual quiet. We are in the productive middle period. Stars burn, planets orbit. On at least one of those planets, living things look up at the sky and wonder. That wondering is perhaps the universe noticing itself. The galaxy, through the unlikely medium of consciousness on a small, rocky world, becoming briefly aware of what it is. Whatever that means, it seems worth taking a moment to appreciate. In December 2021, a remarkable instrument was launched from a spaceport in French Guiana on the northeastern coast of South America. The James Webb Space Telescope folded itself into the nose cone of an Ariane 5 rocket and was carried into space, beginning a 30-day journey to its final position about 1.5 million kilometers from Earth, at a point called the second Lagrange point of the Earth-Sun system, a place where the gravitational influences of the Earth and the Sun balance in a way that allows an object to orbit the Sun in step with the Earth, always remaining on the night side. The James Webb Space Telescope is the most powerful space telescope ever built. It sees primarily in infrared light, wavelengths longer than visible light beyond what human eyes can detect. This allows it to look through the dust clouds that obscure many regions of the universe from optical telescopes. Dust is nearly transparent to infrared light. What would be hidden behind a thick cloud of galactic dust in visible light becomes visible when observed with infrared instruments. When the first images from the James Webb Space Telescope were released to the public in July 2022, they showed the universe in more detail and depth than any previous telescope had revealed. One of those first images showed a region of sky called the ACS0723 galaxy cluster. A cluster of galaxies so massive that its combined gravity acts as a lens, bending and magnifying the light from even more distant galaxies behind it. In this image, what appears as tiny, faint smudges of light are entire galaxies, each containing hundreds of billions of stars, so far away that the light reaching the telescope left them when the universe was only a few 100 million years old. The image covered a patch of sky about the size of a grain of sand, held at arm's length. In that grain of sand-sized patch of sky, the Webb telescope found galaxies beyond counting, stretching back to within the first billion years of the universe's existence. This is what the universe is like. In any direction you look, as far as the most powerful instruments we have can see, there are galaxies. Thousands in every tiny patch of sky. Billions across the whole of the observable universe. each one containing hundreds of billions of stars. The Milky Way is one of those billions. It is, in the cosmic census, a fairly typical large spiral galaxy. Not the biggest, not the smallest, not particularly active, not particularly quiet. Just one among billions doing what spiral galaxies do, turning slowly in the dark, converting gas into stars at a gentle, steady pace, carrying its hundreds of billions of suns through the long, slow arc of its orbit. And yet, it is, from our perspective, the entire sky. Every star you can see with your naked eye is in the Milky Way. Every constellation is made of Milky Way stars. The soft band of light that crosses the sky on clear nights is the Milky Way seen from inside. We are so thoroughly embedded in this one galaxy that all the rest of the universe, all the billions of other galaxies the Webb telescope reveals, appear to us as tiny, faint smudges far beyond the edge of our own. That is a remarkable situation to be in, embedded so deeply in one structure that it becomes your entire visible world, while an enormous universe exists beyond it. The James Webb Space Telescope has also given us new views of regions within the Milky Way. Its infrared eyes have peered into star-forming nebulae and revealed structures hidden from optical telescopes, the intricate inner workings of the clouds where stars are born, pillars of gas and dust being sculpted by the radiation of nearby young stars, protostars glowing at the centers of dense cocoons of material, still gathering mass before they emerge as proper suns. One of the early images showed the Carina Nebula, a vast star-forming region in the southern Milky Way, in infrared light. What had been seen previously as a dramatic but somewhat opaque wall of glowing gas was revealed by Webb to contain structures behind it, dozens of previously hidden young stars and protostars, their warm glow now visible through the dust. The universe keeps offering more at every scale with every improvement in our ability to look. What the Webb telescope is showing us about the very early universe has also been surprising. Galaxies appear to have been forming and growing more rapidly than models predicted in the first few 100 million years after the Big Bang. Astronomers are actively working to understand what this means, whether the models need refinement, whether these early galaxies have properties that allowed faster growth, or whether some combination of factors is at work. Science is always in motion. Our understanding of the universe is not fixed. It grows and deepens and is sometimes surprised. The universe does not always conform to what we expect. It is larger, older, more varied, and more complex than any model has yet fully captured. That is not cause for anxiety. It is cause for quiet, persistent curiosity. The universe is not finished revealing itself. There is always more. There is a Japanese phrase for the Milky Way, Amanogawa, which translates roughly as River of Heaven. It is one of the gentlest names the galaxy has been given. A river, not a road, not a structure, not a band or an arm or a disk. A river, something that flows, something that has a current and a source and a direction. Something that gives life to the land it passes through. Something that you might stand beside in the evening and watch move in the fading light. In Japan, there is a festival called Tanabata, celebrated in July or August depending on the region, based on a story about two celestial beings, Oriheim the weaver and Hikoboshi the cowherd, who are separated by the Milky Way, and can only meet once a year when the two bright stars Vega and Altair on either side of the galaxy seem to come together across it. The festival is associated with wishes and with the bittersweet beauty of reunion and separation. People write wishes on small pieces of paper and hang them from bamboo trees. In the Norse tradition, the Milky Way was called the Bifrost, or at least associated with it, a bridge between the world of mortals and the realm of the gods, a path that allowed passage between different orders of existence. In Hindu tradition, the galaxy was associated with the cosmic river Akash Ganga, the Ganges of the sky, flowing through the heavens as the terrestrial Ganges flows through the land. The Khoi people of southern Africa called the Milky Way the backbone of the night. It is an image that carries remarkable accuracy without any modern astronomical knowledge, because the Milky Way does act structurally in a sense. It is the edge-on view of the galactic disk that gives our night sky its structure, its most prominent, large-scale feature, the backbone of the night. In ancient China, the galaxy was associated with the Silver River, and stories placed it as a boundary between celestial regions, crossed by birds who formed a bridge for the reunion of separated lovers, in a story that parallels the Japanese Tanabata. It is notable that cultures so distant from each other, separated by oceans and centuries, independently arrived at similar metaphors. A river, a road, a bridge, a backbone. Something that connects and divides and carries and gives structure. These metaphors were not wrong. They were attempts to describe something real about the nature of the Milky Way, its span, its continuity, its role as a dominant feature of the night sky, the way it seems to cross from one part of the sky to another like a path. Human beings have been looking up at the same galaxy for hundreds of thousands of years. The stories have changed, the names have changed, the explanations have deepened and refined and become more precise. But the looking has not changed. The experience of lying on your back on a warm night and letting your eyes travel along that pale river of light that has been part of human life for as long as human life has existed. You are part of that continuity. Tonight. When you look up at the Milky Way, you join an uncountably long line of people who have done exactly the same thing, in exactly the same location on the rotating sphere of the Earth, under exactly the same band of light. They had different names for it. They understood it differently. They lived very different lives. But for a moment, looking up, they had the same experience you are having now. Something like awe, something like rest, something like quiet, wide-eyed wonder at the size of things. The night sky is one of the oldest forms of companionship the human species has had. It does not speak, but it is present. It does not change rapidly, but it moves in its slow, seasonal rhythms, always reliably there when the clouds part and the darkness comes. After everything that happened today, whatever it was, the sky is still there. It was there before today began. It will be there after today is forgotten. Let that be a comfort. There are moments in a clear night, if you have found a dark enough sky and allowed your eyes the time to fully adjust, when the sheer quantity of visible stars begins to feel less like a view and more like an environment. Not a flat picture pinned to the inside of a dome, but a depth, a genuine three-dimensional space extending outward in all directions, with you at the center, embedded within it. In those moments, the sensation of looking up sometimes gently becomes the sensation of floating within something. The sky is not above you. You are in it. That shift in feeling, from observer looking up at a distant display to inhabitant embedded within a living cosmic structure, is perhaps the closest most of us will come to a visceral sense of what the astronomy actually describes. We are not on the outside of the universe looking in. We are inside it, wrapped in it, made of it, surrounded by it in every direction at every moment of our lives. The ground beneath your feet is part of the galaxy. The air you breathe, the carbon in your cells, the calcium in your bones, the iron in your blood, the water in your tissues, all of it, every atom of it, is galactic material temporarily arranged into the form of a living being. You do not visit the galaxy, You are the galaxy in one particular local arrangement, and the galaxy for its part simply continues. Stars burn, gas drifts, clouds gather and collapse. New suns kindle in the dark. Old ones slowly cool. The spiral arms sweep on. The central black hole sits quiet. The dark matter halo surrounds it all, invisible and vast. The whole structure turns, one complete revolution every 250 million years, as steady and unhurried as anything that has ever existed. If you are carrying something heavy tonight, if there is something in your mind that will not let go, something unresolved or uncertain or frightening, you do not have to set it down forever. You do not have to have answers. You do not have to be ready for whatever comes next. You simply have to be here in this moment, on this planet, under this sky. You are already doing that. The Milky Way will keep watch through the night. It has done so for 13 billion years. It will do so for billions more. Your particular night, your particular sky, this particular turn of the earth that is bringing the small hours of morning toward you, these belong to a long, long story that was already ancient when the sun was born. Rest inside that. Let the size of things be calming rather than daunting. Let the age of things be steadying rather than humbling. Let the slow, patient turning of the galaxy be a kind of company in the dark. You are here. The stars are there. The universe holds both, quietly, without effort, the way it has always held everything. Sleep well. The Milky Way will still be there in the morning. It always is.